Good morning. This is Unit 2, Day 3 notes. I'm just going to talk a little bit more about polynomials today. It says each monomial in a sum is called a term. Terms of a polynomial written in descending degrees is the standard form. A coefficient is the constant value of each term. The highest degree monomial in the polynomial is the leading term. The constant is the number without a variable. Leading coefficient test using limits. It says power functions eventually rise or fall without bound as x moves towards infinity, left or right. This behavior can be determined by the degree, whether it's even or odd, even or odd degree, also the leading coefficient. The coefficient sign, this one we can see it goes up, down, up. I know that this is a cubic because there's two turning points, so there's 2 plus 1. It's going to be a variable with a third power. The coefficient in this case is going to be positive because the limit as x goes to infinity to the right is positive. The limit as x goes to negative infinity or to the left, it looks like I'm going down, so this one's going to be negative infinity. This coefficient, however, goes down, so this one's going to be negative. This limit as x approaches infinity, or negative infinity, this one is going up, so positive infinity. But this one, as x goes to the right, as x approaches infinity, this one's going down, so this one's negative infinity. This one is going to be an even function, or at least the first term is going to have an even power. This one is going to be, as x goes to negative infinity to the left, my y values go up to infinity. This one's also up to infinity, though, right? It goes up. This coefficient is positive. When they both go down, so that's negative infinity, this coefficient is going to be negative. Okay, a little bit about functions. The end behavior polynomial. Consider this domain and range for each degree family. As x approaches infinity and x approaches negative infinity, what do you notice about f of x, the y value of, or the y value of the graphs? So on even powers, the end behavior is the same. On odd powers, the end behavior, please, sorry, is opposite. And what I mean by that is if you take a look at an even power like y equals x squared, you'll notice that a parabola, they're the same. They both go up. As you go to the left, they go up to infinity. As you go to the right, they go up to infinity. But if you take a look at something that has an odd power, like y equals x cubed, why don't you try to graph this? One's going to go up and one's going to go down. So you guys can tell me what that looks like. How does the value of the leading coefficient affect our limits as we go to the right and to the left? Well, if my leading coefficient is less than 0, then the end behavior changes. Direction. Change. The end behavior directions change. Let's talk about this. So you can use Desmos. I want you to use Desmos. Go to desmos.com. Sketch a graph of the function and determine its end behavior. I want you guys to try B. I'm going to show you what A looks like, okay? So A, it's pretty easy to just graph. It looks something like this. Maybe I should have gone up more. Something like this, right? N is my exponent, and N is odd. A sub N is my coefficient in front of that first term, and this one is negative. As x goes to the right, to the left, negative infinity, my function goes up to infinity. But as x goes to the right, positive infinity, my function goes down to negative infinity. So these are opposite because my power is odd. My turning points, I have 1, 2 turning points. I want you guys to try B. The graph of f has at most n minus 1 turning points. So since my degree was 3, we subtract 1, I know that there's 2 turning points. I'm going down, stopping right here, then I'm going back up, stopping right here, and now I'm going down again. That's a turning point where they change directions. At points at which the graph changes directions from increasing to decreasing or vice versa. The function f has at most n real zeros. So we're going to say at most, it's going to hit the x-axis at most n times. This one only hits the x-axis 1 time, but it's not going to be more than 3. Okay? Even in odd multiplicity, if a polynomial function has a factor that is repeated, these duplicate roots are labeled as multiplicities of n. If f has a real zero of odd multiplicity, then the graph of f will cross the x-axis. But if it's an even multiplicity, it won't cross it, it'll touch it, it'll bounce off and go back up, or bounce off and go back down. I'm going to show you what this means. So let's look at this equation. We have x plus 2 quantity cubed. This is my multiplicity. It's x plus 2 times x plus 2 times x plus 2 3 times. So the multiplicity is 3. So this right here is an odd multiplicity. And my factor is going to touch at right here, negative 2. Negative 2, 0. When we solve for this, we set x plus 2 equal to 0, and then we move the 2 over, subtract it, and that's why it's negative. If we put x minus 1 equal to 0, and we add the 1 over, it's going to be positive 1, 0. It's my other place that it touches the x-axis, my other root, or my other solution. Okay, but this multiplicity is even. Since it's even, it's going to bounce off the axis right here. It's going to bounce off and go back up. Now, since this one is odd, at this point, it's going to cross. It crosses right here. It goes through the x-axis. Let's look at this increasing and decreasing. The function is increasing on the interval if for any 2 x values, the x sub 1 is less than x sub 2, we have the y value is less than, the y value of x sub 1 is less than the y value of x sub 2. The function is increasing when the tangent line has a positive slope. So this function is increasing right here. This is where it's increasing. And this is, we always use the x values, so 2 to infinity. You can include 2. We don't usually, but I have seen both. So I'm just going to use parentheses. Okay. It's decreasing when we have x sub 1 is less than 2. The y value of x sub 1 is greater than the y value of x sub 2. So this right here going down, we have a negative slope right here. This is decreasing. And we always go from left to right. From left to right, we're going down. And this is there's an arrow here, so it's negative infinity all the way to this point, which is -3. Negative infinity to -3. Use parentheses. Finally, it's constant when our x values, for any two x values, our y values are equal. Right here, this is constant right here. And this happens between -3 and 2 on this graph. -3 and 2. Parentheses. The max and min. We have already talked about this a little bit. I just want to review. If f has a local maximum at c, when f of c is greater than f of x, c is called a relative max of f. So this is our max, and this is our max. These are relative maximums. If f has a local min at c, where f at c is less than our function, f of c is called a relative minimum. So this is our minimum. I'll put max on them so you guys can remember. Write it down. This is our maximum. We've already talked about that a little. I want you guys to try this. The intermediate value theorem says, the theorem states that if you can find two values where the sign changes, then a zero of the function will fall in between those two values. Okay? So this is my x-axis. Right here, my value is below the x-axis. So this one, we're going to be at a, I don't know, but my y value is going to be negative. Y value is negative. But right here, at B, my y value is above the x-axis. This is my x-axis, so it's positive. Then somewhere in between here, I know that my graph touches the x-axis right here at C. Okay, it's going to be 0. My y value will be 0. That's what the intermediate value theorem says. You guys can try this one. I'm going to go on to concavity. A function is concave up basically if it looks like a U, guys. If you're going down and then right here we're going back up, this right here is concave up, and it's actually concave up throughout this whole part right here all the way to right here. This is kind of like a turning point. And then for the rest of it, it's concave down, and it's like an upside down U, or like an N, a lowercase n. This is going to be concave down like this. So what I think of is if I poured water in here, this would fill it, this would keep it like a cup. So this is concave up. But if I poured water on this, it would just go down, so it's concave down. And then this point right here where it changes, this blue point right here where it changes is called the point of inflection. The point of inflection. So the function has a point of inflection at C when the graph changes concavity from up to down, or down to up. Okay. I'm just going to go over this example and that'll be it. Use the graph shown below to complete the following. The intervals of increasing. Let's look at this. I'm going to use some of these colors. Intervals of increasing. It looks like it's not increasing right here. It's not increasing right here. Right here to right here, it looks like it's increasing. Is there any other place? Right here to right here, it is increasing, right? So this would be D to E, and we use parentheses on this. And I'm just going to use and. You can use a union also. F to G. Those are increasing. Now decreasing, we're going down. So right here, we're decreasing from A to B. We're also decreasing right here from E to F. One more spot actually, right? There's right here from G to H. These are parentheses, sorry. And comma G to H. I want you guys to tell me what the interval of consistency is. Mark and estimate 2 points of inflection. So the graph is concave down. It looks like it is concave down right here, right? It is also concave down from F to H. So I wanted to just raise it to make sure that that's exactly all concave down. This does not look concave right here down. So what I'm going to do is I'm going to make my own. I'm going to say this is K, and maybe this point right here in the middle is M. So it's really only concave down from D to K. And it's still concave down from M to H, right? So what I'm going to do is write that from D, I'm going to say X is less than or is greater than D and less than K. And the other part is between M and H is concave down. So X is greater than M but less than H. The graph is concave up. It looks like it's concave up right here in between K and M, and I think that is about it. So I'm going to write that between K and M. Make sure I didn't make a mistake on that. The relative maximum values are when X equals, maybe right here is a max. So when X equals E, oh, right here is also relative max when X equals G. So X equals E and G. The relative minimum are going to be right here at F, and I think that's about it. When X equals F. And I'll write min next to it. That is going to be all today. If you guys have any questions, let me know. Have a wonderful day.